Good morning, honors chemistry students. I'd like to take a look at a new problem today, problem 12 from your stoichiometry assignment, which is in essence another version of a mass-mass limiting reagent problem in which you are going to use the masses of starting materials or reactants to predict how much mass of product you can produce. But there's a little twist. You're also going to be asked to determine the mass of reactant that's left unreacted. So to get started on this problem, let's read it in detail. It says, calculate the mass of carbon tetrachloride that can be produced by the reaction of 10 grams of carbon with 100 grams of chlorine. Determine the mass of reactant left unreacted. So to tackle this problem, you're going to need to use the known unknown solution style of problem solving as per usual, which is a standard in my honors chemistry course. Clearly, you're told to calculate the mass of carbon tetrachloride. So you're going to be looking for the mass of Cl4, which is equal to grams of carbon tetrachloride. You should be familiar with Cl4 from your molecular geometry lab in which you modeled this tetrahedral molecule. That being said, it might be helpful for you to actually write the balanced chemical equation in the known section. And you can see that you're producing carbon tetrachloride, right? Correct? It's produced by the reaction of carbon with chlorine. So therefore, you need a balanced chemical reaction. So carbon is going to react with chlorine to produce carbon tetrachloride. Typically, carbon is a solid, chlorine is a gas, and carbon tetrachloride at room temperature is a liquid. You can see that this is not quite balanced because you have one atom of carbon on both sides, 2 atoms of chlorine on the reactant side and 4 on the product side, which means we need a coefficient of 2 in front of the chlorine. You can read this reaction as 1 atom of carbon plus 2 molecules of chlorine produces 1 molecule of carbon tetrachloride, or alternatively, you could read it as 1 mole of carbon atoms plus 2 moles of chlorine molecules produces 1 mole of carbon tetrachloride molecules. Carbon at room temperature is a solid, chlorine is a gas, and as I said before, carbon tetrachloride is a liquid. You may wonder why chlorine is written as a diatomic molecule. Remember that chlorine is a Dr. Hofbrinkel gas. And Dr. Hofbrinkel gases, as I tell my students in honors chemistry, are all those gases that are diatomic in their naturally occurring states, which includes hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, and chlorine. So therefore, we write chlorine as a diatomic molecule. Also, you might note that this is a direct combination reaction in which 2 elements are combining to form a new molecule. And that being said, the last thing you need to identify as well is that you are going to be asked to determine the mass of reactant left unreacted. So you don't know whether carbon or chlorine is the reactant that is going to be in excess or limiting. So therefore, we're going to write this kind of generically by saying that we're looking for the mass of the reactant in excess, which is equal to some value in grams of reactant in excess. You're told that you start with a mass of carbon. And the mass of carbon that you start with is 10.0 grams of carbon. And you're told you're starting with a mass of chlorine gas, and the mass of chlorine is 100.0 grams of chlorine. So armed with that information, you need to predict how much carbon tetrachloride you can actually produce. In terms of a solution, I think it's important to consider how you're going to get from grams of reactant to grams of product. So therefore, whichever reactant is limiting is going to be the reactant that's used to predict the amount of product that you can produce. So we're going to say the grams of limiting reagent or reactant is going to have to be converted to moles of limiting reagent. Whichever one of these two, carbon or chlorine, is limiting, has to be converted has to be converted from grams to moles, because in chemistry we don't compare grams, we compare moles. So once you get to moles of limiting reagent, whichever one of these is limiting, you need to get to moles of carbon tetrachloride and ultimately to grams of carbon tetrachloride. So to go from grams of limiting reagent to moles of limiting reagent, you're going to need to know the molar mass of the limiting reagent. To go from moles of either one of these to moles of carbon tet, you're going to need to know the stoichiometric ratio. And then to go from moles of carbon tet to grams of carbon tet, you're going to need to know the gram molecular mass of carbon tetrachloride. So we have a few things to add to our known section. To calculate moles of each of these, we're going to need to know their molar masses. So on the periodic table, the gram atomic mass of carbon, since it's an element, can be readily found as 12.011 grams of carbon per mole of carbon. And that being said, we also need to calculate the gram molecular mass of chlorine. To do that, I'm going to use my trusty TI-84 calculator, because we know that each atom of chlorine has a mass of 35.453 grams times 2 of those, we'll try that again, 35.453 times 2 gives us a value of 70.906. So that being said, we know that the mass of chlorine is going to be 70.906 grams of Cl2 per mole of Cl2. So we should be able to get from grams of reactant to moles of reactant, but once we get there, we also have to get to moles of carbon tet, and then from moles of carbon tet to grams of carbon tet. So we just may very well need the gram molecular mass of carbon tetrachloride. So I would suggest we go ahead and pencil that in, or ink that in, I might say. So let's do that calculation. Carbon tet has 1 atom of carbon plus 4 atoms of chlorine. So that would be 4 times 35.453, close the parentheses, gives us a value of 153.823. So with that being said, the gram molecular mass of carbon tet is 153.823 grams of carbon tet per mole of carbon tetrachloride. I say carbon tet because in the chemistry trade, that's typically how we refer to it, as carbon tet for short. So armed with that information, we should be able to readily calculate the mass of carbon tetrachloride produced. The first thing we need to consider is which of those two reagents is limiting. So we're going to calculate the limiting reagent. We have to decide, is it carbon or is it chlorine gas? So to do that, there are different ways to do this, but I like to calculate the ideal mole ratio, or the IMR, which is based on the stoichiometric ratio that 1 mole of carbon is consumed with 2 moles of chlorine to produce 1 mole of carbon tet, and compare that to the AMR, which is the actual mole ratio that you have available. So typically when I set this mole ratio up, I like to have the reactant that has the greater number of moles, stoichiometrically speaking. So I'm going to put moles of chlorine on top and moles of carbon on bottom. So we have 2 moles of chlorine for every 1 mole of carbon. So therefore moles cancel out and we're left with an ideal 2-to-1 stoichiometric ratio. That being said, to calculate the actual mole ratio, we approach it in much the same way, except that we're going to use the masses of starting materials to determine how many moles of each of those substances we actually have available. So starting with chlorine, we have 100.0 grams of chlorine, but we need to convert that to moles, so we're going to use the gram molecular mass. We want to get rid of grams, so we're going to put grams in the denominator. 70.906 grams of chlorine, and we're going to put 1 mole in the numerator because we know that 1 mole has a mass of 70.906 grams. Grams of chlorine cancel out and you're left with moles. We're going to do the same thing with carbon, use the same relative approach. We were originally given 10 grams of carbon as our starting material, and we know that 1 mole of carbon has a mass of 12.011 grams of carbon. Again, grams of carbon cancels and we're left with moles of carbon. So we have moles of chlorine over moles of carbon. When we run these numbers, let's quickly do this. We're going to have 100.0 divided by 70.906. That gives us a value of 1.410 moles of chlorine divided by 10.0 divided by 12.011. So the denominator is going to be 0.833 moles of carbon. I rounded up the 2 by dropping the 5 and rounding the 2 to 3. As always, the moles of chlorine and the moles of carbon cancel. And now we have a decision to make. Which of these 2 substances are we going to use to determine, or which of these 2 are going to be our limiting reagent? Well, if the ideal mole ratio is 2-to-1, we need twice as many moles of Cl2 as we do of carbon. So if you doubled the number of moles of carbon, you would need 1.6 at least moles of carbon. I'm sorry, you'd need 1.6 moles of chlorine to have an ideal stoichiometric ratio, which you do not have. And we can verify that because if you actually run the quotient here, 1.410 divided by 0.833 gives you a value of 1.69. 1.69 is obviously less than 2, which says to me that we don't have enough chlorine. So chlorine is going to be our limiting reagent and carbon is going to be our reagent that's in excess. A couple of ways to look at that. How could you get 1.69 to approach 2? You'd either have to increase the amount of the numerator, which means we don't have enough, or decrease the amount of the denominator, which means we have too much. So therefore, we're going to use the 100 grams of chlorine as our limiting reagent for our starting material, which will in essence determine how much carbon tetrachloride we can produce. So the second task is to calculate the grams of CCl4 produced in the product. And to do that, we're going to use our unknown section again and paste this statement into our solution, because we're looking for the mass of carbon tetrachloride and some units of grams of carbon tetrachloride. And in essence, this is going to be another mass problem. So therefore, we would refer to this as a mass limiting reagent problem. We're going to start once again with 100.0 grams of chlorine and convert that to moles of chlorine just as we did above. We'd have 1 mole of chlorine has a mass of 70.906 grams of chlorine. And just tying this in with our solution, we've gone from grams of chlorine to moles of chlorine. Now we need to go to moles of carbon tetrachloride. And to do that, we need to look at the ideal stoichiometric ratio between moles of chlorine and moles of carbon tet produced. So 2 moles of chlorine are consumed to produce 1 mole of carbon tetrachloride. So we want to get rid of moles of Cl2. So we're going to put that in the denominator. And we want moles of CCl4 in the numerator. Moles of chlorine are going to cancel out. Now we're to moles of CCl4. But we don't want moles of CCl4. We want to get to grams of CCl4. So therefore, we need a bridge between moles and grams, which is the gram molecular mass, because we know that there are 153.823 grams of CCl4 and 1 mole of CCl4. So moles of carbon tet cancel, and we're left with grams. So in essence, we've gone from grams of chlorine to grams of carbon tet. Now we need to run that calculation so we can multiply all the numerators and divide them by the product of the denominators. So we can have 100 times 1 times 1 times 153.823 divided by, want the division sign, divided by 70.906 times 2 times 1. And we get a value of 108.46966641. How many of those digits to include would be dependent upon our original measurement. Since the decimal point is present, we come from the Pacific side until you get to the first non-zero digit. Every digit thereafter is significant. So we need 4 sig figs in our answer. So we're going to drop the 6 and round the 4 to a 5. So our answer is going to be 108.5 grams of carbon tetrachloride produced. So that reaction yields, I'm going to use that word yields. We haven't really talked about that vocabulary yet, but we're going to say that that reaction yields that amount of product. Once you understand how much product is produced, the next task then is to calculate the grams of carbon that are consumed. And right now you're probably wondering, why do we need to do that? Well, if our task is to determine the mass of reactant left unreacted, our reactant in excess is carbon. So theoretically, if we're asked how many grams are left over unreacted, we need to calculate how many were actually consumed. We started with 10 grams of carbon. And so therefore you would think that the grams of carbon consumed are going to be something less than 10. So we're going to use this statement, because carbon's in excess. So we're looking for the mass of carbon and some units of grams of carbon. We're going to go ahead and start with grams of chlorine as our limiting reagent. I know that seems a little bit strange, but our task is really to determine how much carbon is consumed by chlorine. So if we know how much chlorine we have to convert grams of chlorine to moles of chlorine, just like we did above, and divide that by 70.906 grams of Cl2. Grams of Cl2 cancel, and now we've gone from grams of chlorine to moles of chlorine. Now we need to get to moles of carbon, and we know that 1 mole of carbon is consumed with every 2 moles of chlorine. So therefore, we want carbon in the numerator because that's the unit we want to achieve, and we want chlorine in the denominator because that's the unit we want to get rid of. So we've made it to moles of chlorine, moles of carbon, but now we want to know mass of carbon. So we've gone from grams of chlorine to moles of chlorine to moles of carbon. Now we want to go to mass of carbon. So we're going to use the gram atomic mass, which is the relationship between mass and moles. We know that 1 mole of carbon has a mass of 12.011 grams of carbon. So moles of carbon are going to cancel. And once again, let's see if we can calculate what the product of this expression is. You're going to multiply all the numerators and divide that by the product of all the denominators. So we're going to start with 100.0 times 1 times 1 times 12 and divide that by 70.906 times 2 times 1, and we get a value of 8.46966. And again, this has 4 sig figs, so our answer should technically have 4 sig figs. So therefore, we're going to round this to 4 sig figs. So we'll drop the 6, the 9 becomes a 0. And the 9 becomes a 0, the 6 rounds to a 7, and the 4 rounds to a, the 6 rounds to a 7. I think it'd be easier to do this on paper. So we have 8.4696 grams of carbon consumed. Since we have 4 sig figs here, we need 4 here. So if we drop this 6, the 9 rounds to a 0, the 6 rounds to a 7. So our answer is going to be 8.470 grams of carbon. And we're going to box that. So that's the amount of carbon that has been consumed. So with that said, the next task is to look at the difference between the mass of carbon you started with and the mass that was consumed. So the fourth and last calculation that we have to do is to calculate the grams of carbon that were in excess, just like the old rock group. So we're looking for the mass of carbon in excess, which is equal to some value of grams of carbon in excess. And we're going to take our original amount, which was 10.0 grams of carbon, and subtract from that 8.470. 8.470 grams of carbon. And as we do that, let's take out our handy dandy TI-84 calculator. 10.0 minus 8 0.470 gives us a value of 1.5300. But you'll note that there's only one decimal place here, and there's 3 here. Whenever you add or subtract measurements in scientific notation, your answer can have no more decimal places and the measurement with the least. So our answer will have just 1 decimal place. And so our answer will be 1.5 grams of carbon. And those are the grams of carbon that are in excess. So in this way, we're able to take a relatively complicated problem and make it a straightforward problem, because you're given masses of starting materials, and on face value, it's hard to envision how chlorine is a limiting reagent when there's 10 times as much chlorine by mass as carbon. But again, we don't compare grams, we compare moles. And so we realize that we don't have that ideal 2-to-1 ratio, so chlorine is our limiting reagent. We use the limiting reagent to predict how much product we can produce in the form of carbon tetrachloride, because grams of limiting reagent are converted to moles of limiting reagent using molar mass, which are converted to moles of carbon tet using the stoichiometric ratio, which is a 1-to-2 ratio. And then we use the gram molecular mass of carbon tet to get to grams. To determine the mass of reactant left unreacted, you first have to determine how much is consumed. So you go back to your limiting reagent, and we say that 100 grams of chlorine consumes a little bit more than 1 mole of chlorine, or a little bit, yeah, more than 1 mole is consumed. And along with that, a given number of moles of carbon, about half as many, right? Times the gram atomic mass of carbon, which gives us 8.470 grams of carbon consumed. And when you subtract that from the original amount of starting material, you can determine the mass of carbon in excess. And with that, that is how you solve a mass-mass limiting reagent problem.